In this lecture, we will prove the strong Markov property for continuous time Markov processes, satisfying the one technical condition on their transition semigroups. Again, here is the statement. We have a Markov transition semigroup of operators on a separable metric space state space S with the following property. There exists a multiplicative system of functions in the continuous bounded functions on the state space, which generates the full Borel sigma field and is preserved by the Markov transition operator for each t. Then if X is a time homogeneous Markov process with that family of transition operators, whose paths are either continuous or at least right continuous, we have the following strong Markov property. For any bounded measurable function on the path space, measurable with respect to the cylinder sigma field, which we now know is the same as the Borel sigma field, at least in the case of the continuous path space, then for any optional time, tau, if we condition that function f of the shifted process x tau plus dot on the augmented sigma field f tau plus, we get the same result as the expected value of that function of the process started at time 0, but starting at x tau, on the event that tau is finite. Now, we already proved a statement like this holds for stopping times tau with countable range, and so our method of proof is going to be approximating the optional time tau with countable valued stopping times, which we showed we can always do. Then we know this equality holds with tau replaced by tau n, and so all we'll need to do is show that as n goes to infinity and tau n converges to tau, we get convergence on both sides of this equation. So let's proceed to do that. We know that the sequence tau n of approximating stopping times decreases to our stopping time tau, and that the augmented stopped sigma field for tau is contained in the stopped sigma field for tau n. We also know that tau n and tau are finite on exactly the same event. Now, since tau n has countable range, we showed 2 lectures ago that conditioning this on f tau n plus gives us the same as the expected value starting endpoint x of f at x dot, where x is taken to be x tau n. Now, the event that tau is less than infinity is the same as the event that tau n is less than infinity, and this event a is f tau n measurable. So that means that if we take the conditional expectation of this on f tau n and then multiply by these, that's the same as conditioning all of this product on f tau n. And then by the Tower property, taking this expectation outside will mean that we have the same thing as taking the expectation outside here. And now we can go ahead and remove that negligible dependence on n on both sides there. Now what we'd like to do is take the limit as n goes to infinity on this side over here. That's going to work under the conditions that we stated in the theorem, but in order to see why, we're going to need initially to restrict to some special functions f, where it's easier to see that this is true, and then extend later. The special f's that we'll choose are going to be cylinder functions. We look only at functions f defined on the path space that really only depend on the path at a finite number of times. That is, f of a path omega is going to be a tensor product function, f1 of omega at time 1 times f2 at omega of time 2 times all the way up to some fk of omega at time k, where the times t1 through tk are chosen from the start, increasing, and the functions are in our presumed multiplicative subset of the continuous bounded functions on the state space. These are, of course, among the bounded measurable functions on the path space. We're going to show that we can take the limit of this as n goes to infinity when f is of this form, and then afterward extend to all the functions that are measurable using Dinkin's multiplicative systems theorem. To see that you can take this limit as n goes to infinity for these functions, we just have to remember how to compute finite dimensional distributions for any Markov process. We can look back to lecture 37.1 for that. If I want to compute the expected value at some starting point x of a function of this form of our process, that's done exactly as follows. First of all, we're starting in measure delta x, so we don't have to integrate with respect to x. We just evaluate there, and what we get is the following. Here, I'm writing mf to denote the operator on bounded functions, multiplication by f. In general, if we had a function of k variables here, we could write this thing as an iterated integral of the transition kernels against that function. But in the special case where it factors as a tensor product like this, as we noted, we can write it in this convenient fashion, where each of these is the transition operator from time t1 up to time t2. Time tk minus 1 up to time tk. This is the essence of how we compute with Markov processes. Now, the reason that we put those conditions on the multiplicative system is apparent from this formulation here. We start with fk at the end, and by assumption, applying q at any time to it produces a new function in M. Now I multiply by another function in M, and because M is a multiplicative system, this is a function in M. And I can continue down the line. So the result of these assumptions is that, therefore, this function of x is in M, which is contained in the continuous bounded functions. That is to say, this function of x is a continuous function of x on this metric space state space. Now we're taking our stochastic process by assumption to have at least right continuous paths, and we know that this sequence tau n of approximating stopping times decreases to its limit tau. And that means that x tau n converges almost surely to x tau. Therefore, by the continuity of this function of x, it follows that evaluating this expected value at x equals x tau n will converge as n goes to infinity to evaluating that at x equals x tau, almost surely. So we get convergence appropriately of this part inside the right-hand side, and then we multiply that sequence by some bounded functions and take the expected value. By the dominated convergence theorem, we'll get that the right-hand side converges as n goes to infinity to the same expression with an x tau here, which is what we hoped for. Now let's look at the left-hand side. Here things are actually a little simpler because of the nice form of the function f. F at x tau n plus dot, by the definition of f, is just this product of functions right here. Now each of these is a continuous function, and as we established on the last slide, x tau n converges almost surely to x tau. Therefore each of these arguments converges almost surely. And so since this is a finite product, we can also conclude that as n goes to infinity, this converges to the same product, but with x taus involved, which is exactly the definition of f at x tau plus. Now we also know that f is this finite product of these functions evaluated at the times ti, and so in particular, the sup of f is less than or equal to the product of the sups of those functions, which is finite and uniformly bounded as n is growing in this evaluation. And so therefore it follows by the dominated convergence theorem in the same manner that the left-hand side converges as n goes to infinity to the same expression with tau n replaced by tau. So just to summarize here, we know from 2 lectures ago, since tau n have countable ranges, that the left-hand side at tau n equals the right-hand side of the desired equality at tau n. We just showed that this converges to the appropriate expression when n goes to infinity, and we showed on the last slide that this converges to the appropriate expression. And so we can therefore conclude that those two things are equal. I'll call that equality star. So we've now proved the strong Markov property holds for cylinder functions. So what we need to do now is show that it holds for all bounded measurable functions. And the way we're going to do that is by a nested application of Dynkin's multiplicative systems theorem. So what multiplicative system will we use? Well, we need a multiplicative system that contains these f's. The multiplicative system we started with was a multiplicative system of functions bounded and continuous on S. Now we need one of functions bounded and continuous on the path space over S. But that's fine. We can take that multiplicative system, which I'll call M twiddle, to be the set of all f's of the form that we considered here. Finite products of tensor product functions of the path at a finite set of times. To be clear, the times and the number of them and the functions are varying throughout this set. It's straightforward to check that that is a multiplicative system. And for Dynkin, we need to have a subspace that contains it. Well, that subset is just going to be the space of all bounded measurable functions on the path space for which this equality holds. Of course, our goal is to show that H tilde is all bounded measurable functions. Now, it's straightforward to check that the constant function 1 is in here. If I just take 1, then the two sides are just equal to the expected value of this event. And also it's easy to check by linearity of expectation that H tilde is a linear subspace of the bounded measurable functions. And finally, it's easy to check using the dominated convergence theorem and the fact that these are uniformly bounded functions f in the definition, that this space H tilde is closed under bounded convergence. Those are all routine, as usual, justified by the dominated convergence theorem. Now, what all our calculations on the last slide and here have shown is that the multiplicative system M twiddle is contained in H twiddle. And therefore, it follows from Dynkin's multiplicative systems theorem that the space of all bounded measurable functions on gamma, measurable with respect to the sigma field generated by this multiplicative system, is contained in H twiddle. That's really close to what we wanted to show, which is that this space with the potentially larger sigma field of all cylinder sets is contained in here. So in order to complete the proof, we now need to show that this cylinder sigma field is actually contained in the sigma field generated by that multiplicative system of functions on the path space. It will actually turn out that these two are equal to each other, but showing this containment is all we need to complete the proof. Now, in order to do that, we remember the definition of the cylinder sigma field. The cylinder sigma field is the sigma field generated by all of the projections. And so, in order to show this containment, it suffices to show that the projections are all measurable with respect to that sigma field. Now, we can show that in a slightly roundabout way by instead showing that for any bounded Borel measurable function on the state space and any t, f composed with that projection, which is a real valued function on the path space, is measurable with respect to this sigma field. And that's going to be enough to show what we need, because in that case we can take f equal to the indicator function of any Borel set. If the claim is true, that will be measurable with respect to that sigma field, which is to say that the preimage of the projection on that Borel set, which is the event that that composition is equal to 1, of course, therefore, must be in that sigma field. But that is what it means to say that pi t is sigma of m tilde measurable, which will complete the proof. So we've reduced the proof to showing that this claim holds true, and the way we're going to prove this claim is again using Dynkin's multiplicative systems theorem. We're going to take a multiplicative system, now the original one, the same one that we started the proof with, multiplicative system inside the continuous bounded functions on the state space, and we'll take H to be the set of all bounded Borel measurable functions on the state space that satisfy this property here in the claim. Our hope is to show that that space H is actually all bounded Borel measurable functions. And to do that, we'll need to check that H and M satisfy the Dynkin properties. M is, of course, a multiplicative system from the assumptions of the theorem. It is, again, routine to check that H contains the constant function 1, since this will then be a constant function which is measurable with respect to every sigma field, and is a subspace and is closed under bounded convergence, both of which follow from the nice robustness properties of measurability in general. Now, if I take a function f in this multiplicative system, then f composed with pi t is in m tilde. M tilde was defined to be the set of finite products of functions of this form. And since that function is in m tilde, it is of course measurable with respect to the minimal sigma field generated by m tilde. So therefore, by construction, M is contained in H. And therefore, by Dynkin's multiplicative systems theorem, the space of all bounded sigma of M measurable functions is contained in H. But the last unused condition in the theorem is that M was chosen so that sigma of M is the full Borel sigma field. So that concludes the proof of this claim. Now let's summarize what we've shown. Using 2 iterations of Dynkin's multiplicative systems theorem, we've shown that for any bounded cylinder measurable function on the path space and any event in f tau plus, the expected value of this random variable on the event A is equal to the expected value of this random variable on the event A. Now, by the averaging property, this is equal to the expected value of the conditional expectation of this random variable given f tau plus times the indicator of the event A, because this is an f tau plus measurable function. Now on the right-hand side over here, notice that this is an explicit function of x tau and is therefore f tau plus measurable because tau is an optional time. We showed that in the last lecture. Of course, this is f tau plus measurable by definition of conditional expectation. So what we've shown is that these 2 random variables here, which are these ones right here, which are both bounded f tau plus measurable random variables, satisfy this identity here, taking the inner product of either one of them with any indicator of an event in A produces the same result. It follows, therefore, that Z1 equals Z2, almost surely. And now finally note that, as we showed 2 lectures ago, tau being an optional time is f tau plus measurable, which means we can move this outside the conditioning. And that becomes the exact statement that we wanted to show, ergo, we have proved the strong Markov property.